Evening everyone, welcome to today's session, problem solving section, week 1, course Applied Accelerated Artificial Intelligence. So first we will summarize the first week lecture and then we will solve the previous year assignment. So first, what is artificial intelligence? So before going to the definition, so in the slides we could have seen that some of the application of the AI includes Amazon Go, that is like a kind of an algorithm or a benchmark which uses AI for like we can go to the shop and take the things and come, the billing will be automatic. The next is retail clothing scenario where like just standing in front of the mirror can try different varieties of the clothes. So what is the artificial intelligence? This is the most accepted definition and published in 2004 by from IBM. So this states that the programs that are intelligence and it is not any rule based or conventional programming method, and it has like vastly evolved from the earlier rule based approach to solve the intelligent problem to the learning based approaches. Next is what is, so it's the making the system intelligent machines and not the rule based one. So deep learning versus machine learning. So, what is deep learning? Any network which has like more than 3 hidden layers or 3 neural layers, we call them as deep neural network. So now what are the computing systems? It can be either a GPU or any FPGA based system or an ASIC or any different kind of a system like TPU, tensor processing unit. So what are the factors for advancement of AI? It is the algorithm has evolved and now we have more data so we can train the model, and as the data increases the compute intensive, it's getting to compute intensive task, so we have a good like hardware. So all the three contributes to the advancement of the AI. So what is the computation need?
Agreed.
Uh, Actually, the deep learning is a subset of machine learning. You can see from this diagram, and the application includes like deep learning, machine learning, natural language processing, text processing, speech, or signal processing. So this graph summarizes. It's a summarized way of representing the different types of algorithm and the computational complexity. So what is this top 5 error? It is like number of samples. If we have like say total n number of samples, we can just say that it's number of samples. Correct label is not in top 5, by the total samples. So say if we have a LeanNet which has 10 output neurons at the output and which classifies the 10 labels. So top 5 prediction will be the first 5 highest confidence predictions. And if the correct label is not in the 5 prediction, divided by the total number of classification or the samples gives the top 5 error. And GOPS is the giga operations per second or gigaflops. So how much this top 5 error is less, that much the prediction accuracy will be good. So to get a linear increase in the accuracy, we need an exponential increase in the computation intensity computations. So next we will look into the computing systems. So we will look into the some of the computing system that are available and what kind of computing system will be suited for the AI benchmark. AI benchmark means which has high computational demand or computational complexity or computational density. So first, it is data intensive, so we need a storage. So for storage, we have like and we have a computational unit and a communication unit between the memory and the computation unit. So next, modern memory hierarchy. So it consists of register files, which you can see runs at sub nanoseconds. So these are the fastest memory, and it is in some words. The size of this register file is very less. Next, we come to L1 cache, which is available in KBs and little more nanoseconds. Then L2 cache, which are available in the storage increases and whereas the speed starts to decrease. So these are the fastest, and coming here this will be the slowest. And this are the main memory, which takes almost some hundreds of nanoseconds, which are DRAM based. And next we have something called as swap disk. So a swap disk or a swap space, this which you are seeing here, which can be in few TBs and which takes some few seconds or like microseconds or milliseconds, are the storage designed for like it's a part of some hardware or SSD, which acts as an extension of the RAM. So it provides a temporary storage to store some, say, an inactive process or data, so that allows the OS to continue running even when the RAM is completely being used. So how do you define compute density? So it's a computational complexity. If means, say I have a fully connected layer, say which has 256 neurons and giving an output of say 120 neurons. So how many additions or multiplications and how many access to the memory it needs to fetch the input as well as the weight, all this contributes to the complexity of the computation. So this you will see like every access to the memory will be taking some amount of power. So okay, next, how to determine how much computing power is required with respect to time or when GPU computation takes place. How to determine suitable for the process. So in the okay, this question I will come later, because we have one slide which shows that how much power is consumed by each of the unit, like addition operation or the memory fetch operation. Now here you see a term called demand paging. So swap disk is to like uh, interchange the like giving some storage to the main memory. Like if this main memory is full, this storage is used, and this is done using demand paging. So like the interchange of the programs between the swap disk and the main memory uh, depends on the availability of the program and is mostly automatic process by this demand paging. And what is demand paging? It is a memory management technique used by the operating system that like loads the necessary part of the program. Now, what is the speed? We have seen the register files are the highest speed, followed by the L1 cache in the range of nanoseconds, and L2 cache in few of the nanoseconds, like many nanoseconds, and little bit more compared to the L2 cache is L3 cache speed, and RAM takes a few hundreds of nanoseconds, and swap disk takes in milli or microseconds, tens of microseconds and milliseconds. And yes, so here we observe that the energy consumed by addition is like very less compared to how much energy it takes when accessing the DRAM for the data. And also the memory access consumes more power compared to the compute units. And so what in the AI task main computations are like multiplication, addition, and accumulation, and the uh, data transfer from the register file or the cache. This SRAM is the cache and DRAM is from the main memory. Next, modern system. Why we are going for this memory hierarchy? Like how this hierarchy of memory is helpful.
Hey, I can answer it.
Yes, please.
For training the models, right, we need a lot of data, and for computation purposes, faster we can access the data, faster the training process and inference process would be.
Yes. So this hierarchy gives an illusion that we have a very large storage which is of high speed. And as you mentioned, AI benchmarks, we need a lot of data, and AI algorithms are like extremely data hungry. So memory access is a key factor, and it is also consuming more energy. It consumes more energy. So if the memory access increases, energy will increase, heat will increase, and also we need cooling systems. So modern memory systems, every core internally it consists of a L1 cache and also an L2 cache. L3 cache is shared, and DRAM is like a higher memory. So it's shown separately. It's a higher memory density. Next, this is a wafer scale AI accelerator. So like it's the whole complete wafer is one accelerator. So it's a wafer scale engine. This is like one complete 1 ml compute engine. It consists of 400,000 cores and 18 GB of on-chip memory and access speed of 9 petabytes per second memory bandwidth. So you can see it has massive number of transistors, and this is from 2019, and the next version from 2021, which has almost double the transistors. So next, computation speed limiting. We cannot go on increasing the clock frequency because of the power factor, the Dennard scaling. So we are having like the clock frequency is like saturating. If we increase the clock frequency, the number of computations will increase, but we cannot go on increasing the clock frequency. And so hence, how can we like overcome these bottlenecks. So how can we do this high computational density work? So we have a specific GPU to offload the like perform the AI specialized task, which are can be done in parallel, and the CPU x86 CPU, which can perform the other serial operations. So which are not that much data intensive task, can be executed in the processor itself, and which can be computed parallelly will can be given to the GPU. So GPU acts like a coprocessor. So here we have the specialized computation engines like from ASIC, which are specialized for the AI benchmarks, and the other GPUs, which are for AI benchmark as well as for the like generalized for video or graphics. Now, next evolution of NVIDIA's GPU. So the number of functional unit increases, and also the gigaflops per second, the computation power increases. So increase in the number of the functional unit increases the performance. These are the slides directly taken from the NPTEL. So, okay, this power, I think this graph explains like how each unit consumes the power. I mean, how to determine how much computing power is required with respect to time, or when GPU computation takes place, how to determine how much will be suitable for the process. Next, we see two versions of the NVIDIA GPU, Volta series and the Ampere series. So this NVIDIA's Volta series V100 is like released in 2017, and Ampere series from 2020. And we observe that it consists of 680 cores with 64. Yes, this section is I'm recording section. So we have 18 to 64, 5120 steam processors, and 108 into 64, 6912 steam processors. And here we have an L1 cache. I think it's L1, L2. L2 cache, and here we have splitted the L2 cache, the difference from the Volta series as well as from the Ampere series. So in the Ampere series, the L2 cache is now in kind of like two banks. So L2 cache 1 and L2 cache 2. And this is just to like increase the throughput or reduce the latency of reduce the latency of the memory. NVIDIA V100 core. So this it consists of single precision is like 32-bit FP data type, and double precision is like 64-bit floating point representation. So like a 4 cross 4 multiplication using FP16 and addition. So of one 4 cross 4 matrix multiplication will be done like uh, in one clock cycle, and the matrix multiplication is the like important computation in any AI benchmark. So this convolutional neural network, if we say the computation mainly uh, based on the matrix multiplication, general matrix multiplication. So the acceleration, each core performs this multiplication in one clock cycle. Next, from the Ampere series, you can see the core count is increased, and it supports the 32-bit unit. So 32 bits fixed point floating point and 64-bit floating point. So this is like with respect to the architecture. Now, GPU based accelerator. So the various data type it can support. So this is an FPGA based accelerator. FPGA stands for field programmable gate array. Now the TPU, which is from Google, Tensor Processing Unit, and version 1 is mainly for the inferencing. Now version 2 and 3 are for Google data centers or large scale deep neural network training. So version 1 is only for the inference. And all these computation engines are essentially array of processing elements arranged like in a form of a systolic array based engine, and like processing element which is like a MAC unit or a multiple combination like collective of MAC unit. So here we have a collection of 14 cross 12 processing element. This is the first version of the TPU. And so we have the off-chip DRAM and scratchpad memory of 108 KBs. This processor achieves little like much higher throughput, and you can see how much milliwatt of power it is consuming. So FPGA based are consuming power in milliwatt range, whereas you can see GPU consumes in the watt. So typical FPGA based accelerators. So mainly if you see the systolic array based architecture, it reuses the data. Once we fetch say the weight values, it is reused in the like multiple columns of the systolic array. Based on the data flow it is using. So in this way it is like slightly reducing the memory access. Say the data it has fetched here will be applied from to a register file to this through a register to the next processing element. So the data is reused. Next, the market share. Nvidia based GPUs share the maximum, and next is from AMD. The FPGA based maximum share uh, by the Xilinx, then the Ultra, Microsemi, and Lattice Semiconductor. So now, what is the gap? To like we have seen to get a increase in the accuracy, linear increase in the accuracy, we have an exponential increase in the computation density. And the next is we cannot go on increasing the clock frequency, and the memory access consumes a lot of power. So now the computational requirement, which is like increasing exponentially, and the resources available that like everything the resource available and the trend is getting saturated because of the feature size. Almost we have when it came till 8 nanometer and like almost in 1 nanometer, so we cannot decrease the feature size below this. So how can we bridge this gap? We want to accelerate the AI benchmarks. So this computational requirement which is increasing exponentially, whereas the performance density is saturated. So we will see how to use the existing computational uh, to achieve this increase the performance. So these are the links for the memory system and the neural network and coprocessor. Next, we will see what are the AI accelerators and where they are used, how they are used, and the GPU, CPU, and its benefits. So what are the artificial intelligence accelerators? So we have seen that one is FPGA based or the ASIC based, and the next is the general one which can be used for AI task or any video or signal processing application, which is the GPU one, and the next is the CPU, the main processor. So this will be like a co-processor, and CPU, the main processor. So mainly we divide into two tasks. Now edge devices will be mainly performing the inference, and data center say it's performing the training. So this edge devices should be like a smaller device capable of like performing the inference operation with lesser power and limited resources. Data centers, whereas can be used for the training with massive cooling systems. So now how do we like have, like say we have CPU, the data intensive work, we transfer it to the parallel processing uh, coprocessor and get the results and again transfer to the CPU. So host we call as the CPU and the device is our GPU. So the compute intensive tasks are offloaded to the say this GPU. So one view of the AI accelerator, uh, CPU, we have a GPU, FPGA, and a vector processing unit. Say we have a serial task as well as a parallel task, and the data parallel workload can be run in the say in the coprocessors like FPGA1 or the VPU, and the serial task can be run effectively in the CPU, and the serial and parallel task can be run in CPU and GPU. So the CPU and GPU, to communicate we need a protocol. So they use PCI Express protocol. And next, this is a demo showing the like this command to display the CPU information and this command to display the GPU related information. Okay, next task and data parallelism. So in the data parallelism, the data is there is a data decomposition. So data is divided and given to the different tasks and then combined. In the task level parallelism, decomposition is at the task level. So the same data is given to two different tasks. Like this block of data goes to this task and this block of data goes to say this task and the third block goes to the third task, and you like we aggregate this all these results, and this data parallelism, like this is called as like the data parallelism. Next, the task level parallelism, it is the like mainly this task or parallelism is at which level the decomposition is at which level. So if it is at the task level it is called task parallelism, and if it is at the data level it is called data parallelism. Next, applications. uh, yes, this presentation will be available, and The recorded section will be also uploaded in the uh, Google, sorry, YouTube, and the link will be shared in the Excel sheet provided to you. Uh, most of the Yes, this is from the week 1 NPTEL content. Same slides I have taken just for summarizing, and the previous year assignment questions we will just solve. Next, still most of the AI companies are using NVIDIA's GPU compared with Cerebras Y. So NVIDIA offers some user like coding uh, frameworks that you can use to code to use their, say if Google TPU, you can use TensorFlow Lite to accelerate your design. So similarly for NVIDIA, we have that CUDA, CUDNN, and this frameworks which you can use it to accelerate the NVIDIA. So such frameworks, once it gets developed for the other AI accelerators, then it will also be widely used. Because we have a framework where like I have an AI task, I can just accelerate it on a particular hardware because say I have a TPU architecture which has 2 cross 2 systolic array. So now to accelerate this, my code, say the Python code, to run this particular, say a fully connected layer in this TPU or the systolic array architecture, it should be giving the data, say input here and loading the weights here. Then only like the task can be accelerated. So for that we have frameworks. For the TPU like TensorFlow Lite provides some options, and for the NVIDIA GPU we have the CUDA or the CUDN and so. Yes. So this data are taken from the paper cited below for the FPGA. I think FPGA 1 is from 21 and this is also from 21. The slides are directly taken from the NPTEL. So now what is the difference between the CPU and the GPU? Say for CPU, it consists of multiple cores and we have an L1 cache for each of the core. We have a control unit for each of these cores, and then we have an L2 cache, L3 cache, and a DRAM. For a GPU, it is a huge, massive parallel processing cores, and they have got their own control and cache. And then we have an L2 cache, and then we have a dynamic RAM. So it consists of a massive core so that it can perform the task parallelly. So the way it is programmed is little bit differently so that we can achieve the maximum acceleration. So this is the difference between the GPU and the CPU. So GPU for the data centers and the edge. So GPU supports like massive parallel programming. So GPU for the data center is a similar family of GPU. For the edge, now how many cores we want, a little for that application, and the connectivity between the CPU and the GPU. Now it is completely in an embedded type. So say uh, Jetson Exever NX processor engine requires like also requires an high speed IO and memory fabric. Okay, so now if we have any sequential task, so this is performed can be performed in the CPU. So to perform this operation, we need this result. Whereas for GPU, we can convert it to parallel and run multiple tasks in the parallel. So say we start n by 2 threads and one thread for every two elements. In this way, we can perform the task parallelly and reduce the time. This is CPU versus GPU training time. So the CPU takes higher time compared to the GPU. That's fine. Now train a convolution neural network on multiple GPU with tensor. Okay. So instead of one GPU, if you want two GPUs, then the values can be given is given to the GPU to calculate the gradient, the loss, and update this model, and it's given back to the CPU. So it's done from the multiple GPUs. So this is from IIT Varanasi, a cluster that consists of 837 teraflops and the configuration. And this is the configuration for DGX. So here we have an NVLink, is a proprietary bus link developed by the NVIDIA and which uses, and it consists of 8 GPUs and a PCI Express for communication between with the CPU. So next, yes, this is the DGX, how it performs the computation parallelly. So how to use this tensor course? We have the CUDA libraries, tensor course CUDA libraries, and this uses the tensor code to speed up the GEM computation. GEM is the general matrix multiplication, which you can use for both convolution and fully connected convolutions. So yes, because NVIDIA provides this libraries and framework, it is like widely used. Next, this we can see without tensor core, it takes more time compared to running on the GPU with tensor cores. Okay, next. We will see about the operating system. So, what are the privileges that an operating system or the software or application software wants to access? And we will see about the virtualization and learn the underlying technologies or the methodologies that are available for the virtualization. So let's start. Operating system is a piece of a software. So we have a user application and an operating system. The main difference is how like something will in the memory. So the operating system is a software and it has most of the privileged privileges in the computer systems. So privilege means now operating system can do special things which the user software or the application user application cannot do. So what is this privilege? Access means writing to the disk, accessing the network card or the memory controlling these hierarchy CPU usage. So what happens when we have multiple programs and we want to share this hardware? This hardware means the resources, the memory, the compute system or the IO system. So the application program wants to access this hardware. The interface between the hardware and the operating system is called as instruction set architecture. And so that this software talks to this hardware using this interface, which is the ISA. So if any program wants to access the memory or store some files to the CPU, it has to it is controlled using this instruction set architecture. And now the two program wants to access the say some IO. Say program 1 needs to access the memory and say the program 2 wants to access the network card. To control this provides the drivers provides the multiplexing and is done through the ISA. And so software layers. Now if we are running like several programs, the user level program, which is like operating system, which has several libraries and other protection modules, the multiplexer scheduling module, every etc. So all these softwares are lying layer wise inside the system. So you have a user space and all the processes will be running. So processes means the user applications. Then we have the operating system, the user application followed by the operating system, which performs the scheduling and say scheduling the memory management file system. Now in between user space, all the process will be happening through the system call interface through the OS. So this interface is we will understand next in the virtualization. So say one process wants to access some memory or the file system which is residing in the hard disk. So the process will invoke a system call to the operating system, and then the operating system will convert this instruction set architecture to several components as user components and as well as the system components. But the instruction set architecture and that will eventually go to the underlying hardware. Now increasingly in this stack, one more layer we are adding, which is called as hypervisor, which is widely known as a virtualization layer. So hypervisor is also a piece of software. It is below the operating system. Yes. Next we will see what is this hypervisor. These are the Okay, these are the various interfaces in the computing system. It is from API, ISA, or ABI. Now, virtualization makes the real system appear to be a set of virtual system. So, one-to-many virtualization, many-to-one virtualization. So, if we have one physical machine, may appear as a multiple virtual machines. Okay, so let's get into what is VM. What are the different type of virtual machines? So here the idea will be like where we can virtualize and what level of virtualization we can do and what are the advantages and the disadvantages. So we have seen hardware on top of that operating system, and this interface we called as instruction set architecture. So in the hardware, like say x86, it is called as x86 ISA. And we have seen the ABI, which is the system call interface, and boundary between the application process and the hardware. So what are the different type of virtual machines? Here we are performing the virtualization. So there are some application process. Between the hardware and software, we have one ISA, and so it virtualizes this ABI, which is the application binary interface, and the system. This is the process virtual machine and the system virtual machine. Here, the virtualization is after the operating system. What are the benefits of virtualization for the user? So if I have two programs, application programs, both the programs has the illusion of having the complete hardware. What is it? Speed or other processes. So that scheduling is taken care by based on the virtualization and the hypervisors. So, and not all the resources are going to be used at the same time by one process or one application. So, at the same, that can be used by the another application. Let's just discuss these two types of virtualizations. Now, say if you want to run any applications, virtualizing software, one new ISA you want to try, say like want to virtualize one software. So from this ISA, the ISA conversion introduces one new virtualization software that will emulate the conversion of this ISA and this ISA. So now let us say JVM, Java Virtual Machine, writes a program in Java program. Say we write a Java program which will be actually compiled to bytecode and which will run only in the Java virtual machine. So Java virtual machine is a virtual machine which will transform the ISI bytecode to the x86 ISI. So interface between this this ISI and x86 ISI. So the advantage of this process level virtual machine is that we are talking at the process process VMs, that we are virtualizing this ABI. So ABI was the interface combination of the system calls between 2 and ABI is 2 and 7. Sorry, API is 2 and 7. Sorry, it should be 3 and 7. It virtualizes API 3 and 7. So now virtualizing software or the process level software is essential for virtualizing this API. So the new ISI API, this translation is done by the virtualizing software and it will perform the binary translation. So the advantage of this virtualization, virtualizing the process at the process level, where if you want to run this application processing to another system, let us say some ARM system, and if you want to run on like any other system, like say ARM or a Power PC or other system, having this virtualization software installed, we cannot we don't want to change anything inside this application process, as it will directly run on the bytecode or the bytecode interface that will be provided by the virtualizing software. That bytecode is example in this case. Now application process is just seeing this ISA that is being interfaced between provided by this virtual machine. So this is no longer dependent on the application binary interface. Now, system virtual machines are virtual machine which visualizes the ISA itself. So this process, which is virtualizing the ABI here in the system level or the system level virtual machines, we are virtualizing this ISI itself. So now ISI means the one underlying interface between the OS and the hardware. Basically, the ISA now, like we are virtualizing this ISA. So the virtualizing software will run in privilege mode. So basically, this will query this hardware for privileged instructions. And the hardware, this interface between the virtual software, the VM system level, and on top of that the operating system and the application. So operating system and application is looking at this interface, which is the system interface, and let us say the ISA. So you know this is the ABI for the application, and this is the system interface for the ISA and the operating system. So now the operating system will be privileged instructions as it was doing in the native hardware, but now using the virtualization software, it translates the ISI to another ISA interface. So let us say x86 ISA interface and the ARM ISA interface. Now the system level virtualization software is translating this privilege modes and converting the ISA from the interface to this interface. OS does not know, because the OS is looking at this interface, and that is completely like okay for the OS, that the underlying hardware was supposed to be an x86 ISA. Now what the virtualization software is doing is that, so whenever the OS is sending or assigning the privileged instruction, it is taking that instruction and emulating them in the underlying hardware, and then returning the calls to the operating system. So there will be some resources used by this because of the emulation will cost some hardware and resources, but the main thing, important thing is that now the operating system, this world of have this operating system, it is completely unaware of the underlying hardware, that interface. So let's see in little detail. So system VMs is detail. VMs or the system virtual machines are also called as hypervisors or the virtual machine monitors. So whenever VMM or hypervisor means that system of virtual machines that is running underneath. So what is hypervisor? Hypervisor is an operating system, um, hardware, and like we can see that we have an hardware, and when we boot this entire system, the first thing gets booted is this hypervisor, and then you have multiple operating systems which will be sharing this underlying hardware through this hypervisor. But this virtual machine will have different operating systems, say guest operating system 1, 2, and 3. Now this hypervisor will get booted up initially or in the beginning, and then OS1 will be booted up followed by this 2 and the 3. So hypervisor is essentially providing a virtual execution environment for the entire operating system and its application, which are running on top of the OS. So the advantage and the main like different between this hypervisor or the operating system in the computer system viewpoint we will be seeing further. So because we have this operating system alone on top of the hardware, and the OS is supposed to get booted up in the beginning itself, if we don't have this hypervisor, and after that guest OS will be booted up on this different virtual machines. The key difference is that hypervisor here will be like not visible. It will be a transparent, completely transparent. If you see the operating system, it, let us say, will try to access the hardware through several privileged instructions, and say the file access or trying to access the network. It will initiate this privilege instructions from the operating system to the hardware, and that will be going to the hypervisor, but it will be completely transparent and not known to the operating system. So now it is like invisible what this hypervisor could try to do, that it will trap those privilege instruction and then it will emulate in the underlying hardware. This underlying hardware which is in this underlying hardware. So guest operating system does not know like what is happening below. So it was supposed say try to access the memory and say another or maybe disk or the network interface, then it will, or maybe let's say the IO device, it will if you want to access, it wants to try to access, then it will initiate this privilege instruction, and then the hypervisor will emulate this in the underlying hardware. And this flexibility of using this hypervisor on completely transparent system between this operating system and the hardware, so that all the privilege instructions are coming from different virtual machine, hypervisor can now schedule them to the underlying resources. The hypervisor is completely doing the same thing as the operating system was supposed to do, the scheduling or the resource management. So everything hypervisor is now doing the same thing, but the virtual machine that is on top of that. So like, the guest OS gets executing the gets executed the privilege instruction. Hypervisor intercepts the instruction and checks for the correctness, then emulates the instruction on the underlying hardware. So what are the different types of hypervisor? Type 1 hypervisor, which is bare metal or native. Type 1, the hypervisor is lying on top of the hardware, so that's why like bare metal, and then it is kind of trapping all the privileged instruction coming from the virtual machine, say VM1 or VM2, uh, VM1 VM2's guest operating system and application, and running completely in separate like different environment. So VMware has different hypervisors for different machine, like uh, say VMware ESX, basically a VMware that has different hypervisor for different machines like desktop or server. So basically VMware ESX is server level system hypervisor, and Zen provides system level hypervisor, which is type 1 hypervisor. So this hypervisor is like completely transparent. So the virtual machine or the guest OS which is running in the virtual machine, they will do initiate this privileged instructions to this hypervisor, and they will not know like what the hypervisor is like completely transparent, and the hypervisor underlying that will trap them and emulate them and get back uh, to this one. So we are seeing this. Okay, let's see. In the hypervisor too, there are some instructions which will be directly accessed by the operating system and some through the hypervisor. Uh, like which hypervisor 2 kind of hosted on the native operating system, so that it is called as the hosted virtual machine. Now the native operating system, say like the virtual machine that can be on the top of the type 2, and all this privilege instruction coming from this guest OS can be emulated by the hypervisor. So here the hypervisor needs to write for this complete hardware, but in the type 2 hypervisor we require only like little lesser effort, because you are writing for the not from the scratch all the drivers for controlling the underlying hardware. That is the difference. And para virtualized virtual machines, with another set of virtual machines. So here the virtual machine, we have seen that modifying the guest OS will give better performance for the para virtualized virtual machines, because if we see the traditional hypervisor, which is like fully virtualized. So so basically they expose the virtual machine to the virtual hardware through this, which is like fully underlying hardware. Advantage is that we need not modify the guest OS. So the guest OS can run as it is, because it does not know that there is an underlying hypervisor running like it's completely hypervisor is completely transparent. But the disadvantage is that hypervisor is sensitive, that sensitive instructions will also get trapped and emulated by the hypervisor, and all the sensitive instruction that are coming from the guest OS are trapped and emulating them will cost these resources. So virtualization like kernel level virtual machine or KMware, VMware, ESX that we have seen. So instead of like providing all full virtualization, uh, the para virtualized VM sees a virtual hardware abstraction that is similar to this but not actually the real hardware. So here the guest OS is modified with replacing some calls, sensitive instruction calls. So basically you like the hardware hypervisor and the OS. If the hypervisor wants to get fully transparent, then all the instruction privilege coming from the OS gets trapped into the hypervisor and simulated. And say if I don't want all the instruction to get emulated inside the hypervisor, rather some sensitive instruction or define one set of instruction which execute through this hypercalls to the hypervisor. So now hypervisor is no longer like transparent in this. So now the operating system knows that this set of instruction or this set of sensitive instruction will be through the hypercall to the hypervisor, and this set of instruction will be through the normal system call. So this way of the hypervisor is like now here no longer completely transparent. Rather, like it can capture some of the sensitive instruction through this hypercalls. So there will be an interface of this hyper call interface. Okay, so let's just go to the examples. So these are some of the hypervisor examples. I think this three type of hypervisor is clear, where type 1 we have to write it completely from scratch, and every guest OS was going through the hypervisor. Here the guest OS is coming through the hypervisor, then the operating system. So we need not write everything from scratch. And here the hypervisors were transparent. So now here the operating system knows that this set of instruction uh, this set of instruction is going to be run by the hypervisor, and this from the normal system calls. So these are three types of hypervisors. So now this is host OS and hypervisor. We have a traditional process. So let us say that hardware, the host OS, and similarly some of the process running on top of that. This process are sharing this underlying resources, and complete multiplexing is happening inside this operating system to share the resources between the process. So they may be taking one or a few threads, and all this will be actually controlled by the operating system directly to have access to this privilege instruction for the hardware access. Now for isolation, the process can see all the resources that is available, but some virtualization or multiplexing that is done by this OS in this level of multiplexing, uh, like we can see that several processes will be there, but we can see that entire resources are forbidden, but the OS will handle which portion will go to which and to whom, and which resources will be allotted for which process. So if say This is like it is loosely isolated. We can see that because these processes will be talking to the OS through the system calls, and they have, let us say, 400 near 400 system calls in Linux. Now this all these system calls available for the process that is available on top. That means it is like loosely isolated. So this is one extreme and spectrum, and in the spectrum another is extreme traditional virtual machines. So hypervisor will be there on top of in the virtual machine, which we will say like guest OS 1, guest OS 2, and on top of that similarly some process running. Now this process running on this guest OS will have no idea of what kind of resources, or there is an isolation between this process. And so the two guest OS is like completely rigid. The resources that have been shared between the guest OS are completely managed by the hypervisor. So there is a complete isolation of how much disk or the resource that will be accessed by this virtual machine or the guest OS. So all these guest OS will see the hardware, and this process will only know that whatever system calls that this process invoking for this guest OS. No other system call will be there inside the guest OS, because these process system calls will be routed through this guest OS, which is completely from virtual machine. So the isolation here is like completely rigid. System VMs. So the system virtual machine, we can see that virtual machine has its own guest OS, own guest physical memory, which is virtualized. So isolation is important. Isolation of this process are very important because with the increase in the workload of different application domains, some process need isolated completely from the other set of application. So limiting what we want to process, who will like take how much resources, these processes can share. So all these are very necessary in terms of the isolation. So the process that are sharing the like the great isolation will provided by the system level virtualization through this multiple isolated user space and sharing of one kernel and native performance. So, process virtual machine and containers. So this is one way of virtualizing things, but the thing is here we are containerizing several processes which we think that these processes can talk to each other, but they need to be completely separate from or like should be some isolation between this set of processes and this set of processes, and these are called containers. And this container concept was from 2008, from when Linux operating system started using the namespaces, because processes share namespaces. So if you contain the process in terms of namespaces and control groups. So in this concept, the virtualization cannot have high or rigid, like still there is a container in one process, because container will invoke system calls to this host operating system, and then the host operating system to the hardware, and also this container will invoke the system calls to resource OS, and so on and so forth. So in terms of virtual machines, so fully virtualized virtual machine or the system level virtual machines, uh, we cannot get this much of like isolations. But since we have much more resources which are allocated for the full isolation of the process, like we can have big resource gain in this approach or the container based approaches, where uh, a kind of namespace separated between these processes and a kind of isolation executed or isolated resource sharing between these containers. uh, Cloud computing. Okay, this. So this brings us to the concept of cloud computing. Uh, we have talked about virtualization at different levels. Now, if we can virtualize everything, like the processing, if we want to virtualize, if we want to virtualize the storage or the software resource, that means we have seen all the software resources on the entire software stack. So if we want to virtualize that in terms of packing everything into one resource and share the resource, now share the resource the entire. No, this I have taken screenshot from the NPTEL lectures. Okay, let's just start the service models. So the infrastructure as a service, we can manage the application data runtime, middleware, and operating system, and we don't have access for virtualization, server, storage, and networking. Whereas at the platform level, application and data is only accessible. And when we get a software, it is as a service alone, and we cannot access the entire stack. So, say the cloud provider, Microsoft Azure is an IaaS, and so at this level, which includes Google App Engines, at the software level, we have softwares like such as say Gmail. So let's go into the previous year assignment questions. Which cloud computing service model allows user to access computing resources such as storage, networking, and servers? And server or service? So at the platform level, it provides the platform without dealing with any of the underlying infrastructure. At the software level, it gives the software application over the internet, just the application. And at the data as a service, it provides the data on the demand of access, like on demand access to the data. So it is the instruction as a service, which provides user with the fundamental computing resources such as virtual machine storage and networking and the servers. So user can manage and control the operating system application storage, but not the underlying cloud infrastructure. So the correct answer is IaaS. The next, what are the significant factors that have contributed to the advancement of AI? So the uh, advancement in the algorithmic level, the increase of the data available, so that now the training is also possible with the increase in the data, advancement in the data, and the amount of compute available for the training. So with the advancement in the hardware, so all the three contributes to the advancement in the AI. So the answer is 1, 2. Next, uh, what is the operating system for operating system, which provides a virtual execution environment for the entire operating system and its application? Yes, it is VMM, virtual machine monitor, the hypervisor, which is a software that creates and manages the virtual machines by providing a virtual execution environment for the like entire operating system and the application. So it acts as an operating system for the operating system, allowing multiple OS instances to run on a single physical machine. So each machine will be like having its own CPU, memory, storage, and network interface. So what is the kernel? Kernel is like a core part of the OS that manages system resources. And next is the middleware, that is a software that connects different application or services. So it is like not in the OS virtualization. API, we have seen application programming interface, a set of tools and definitions that allow system, software to communicate and not related to the OS virtualization. The correct answer is hypervisors. So next, Microsoft Azure is an example of uh, we have seen Microsoft Azure is from IaaS. Yes, correct. Mm, why? Because Microsoft Azure provides virtual machine, that is like storage, networking, and computing resources. So it should be in the instruction as a service. Next, in which VM virtual machine monitors translates the ISA used by one hardware platform to that of the another. Yes, this is previous year week 1 assignment. So the answer is system VM. What is process VM? It is designed to run a uh, single process or say an application, and it abstracts only the execution environment that process, like example JVM. It doesn't handle the low level instruction set architecture translations. And next, high level language VM executes program written in a specific language like say Java. It operates above the ISC level and doesn't deal with the hardware ISC translations. Now, what is dynamic translators? A technique. Uh, it's not like a type of VM, but a binary translation is often used within the system VMs when the hardware ISA doesn't match that of the guest OS. But it's not a like, so it's a system VM. So which has the highest performance in the modern hierarchy? So we are seeing the hierarchy. We have register file followed by L1 cache, L2, L3 cache, then the main memory, and then the swap disk. So the one which is in the last has highest storage but lowest performance, and at the top has the, say this has high storage and low performance. Low performance means speed. Access access speed is high, and this has low storage, say in few words, and has a few words of storage and is high speed. So this, so next question. Hosted VMs are also called as, yes, hosted VMs are type 2 hypervisors. So these are the virtual machines that run on top of the host OS, like meaning that the virtualization layer is installed as a application above, like on the existing OS. So which of the following is the GPU execution model? So multiple instruction, say multiple instruction, multiple data is, I have set of instruction, set of data. So used in CPU and distributed system when different processes executes different instruction on different data. So this is not for the GPU. Next, SISD is like one instruction, one data. So sequential computing, so say sequential CPU. And SIMD is like we have multiple instruction on same data. So say I have performing a plus, say 5 plus 5, again 5 plus 5. That means maybe for a fault tolerant, not in GPU. Then SIMT, single instruction, multiple threads. uh, that is single instruction is issued to multiple threads simultaneously. So this is used in the GPU. So each thread executes simultaneously the same instruction but operates on different data. So this allows efficient parallelism for the graphics rendering or say video processing. Next question. What does the hypervisor typically do when a guest OS executes a privileged instruction? Yes, it interprets the instruction, checks the correctness, and then emulates. So hypervisor is like completely transparent, so it has to take that instruction, check the correctness, and then execute. Next. Which one of the below is used by the user program to request services for the operating system? So the user ISA is a set of instruction available to the user level programs. And what is system ISA? It is the instruction available to the OS kernel or the privileged mode. Next, hypercall is used by the guest OS to request service from the hypervisor in the virtualized environment. And what is system call? It is the mechanism used by the user program to request services from the OS, say any file operation, any IO, etc. So it acts as an interface between the user application and the OS. So the correct answer is user and the operating system is a system call. So any doubts? So if no doubts, then I just stop the recording. I will wait for few minutes.